So as we had discussed in the previous lecture that images are often corrupted by different kinds of noises. So assume that we have an original image f represented by f of x comma y, where x comma y is a coordinate of a particular pixel. So we are using a Cartesian coordinate system without being specific about whether it is a left-hand Cartesian coordinate system or right-hand Cartesian coordinate system, because it wouldn't affect our discussion at all. So assume that we have the original image signal represented by f of x comma y. And it is corrupted by some additive noise. So additive noise are the kind of noises that just add upon the original pixel values. So this is a small noise, epsilon, at location x comma y. So we are assuming that this noise is additive, and furthermore, as we had discussed earlier, that we are going to only discuss noises that are spatially independent, that is, they do not depend on the pixel value, and also they do not depend on the values of pixel in the neighborhood of a pixel x comma y. So after adding the noise, we get our image I of x comma y. So I of x comma y is our resultant image after the addition of the noise. Resultant image after noise addition. So the different distribution models. So since this is a random noise, a small random noise. So depending on the distribution that this noise follows, we have different noise models. So for example, a uniform noise model will have a uniform distributed noise. A Gaussian noise model will have a Gaussian noise. And likewise, the impulse noise model, in the impulse noise, in the fixed value impulse noise model, the noise doesn't follow any distribution, as we'll discuss later. But in the random valued impulse noise, this noise can follow one of the many distributions as well. So in this video, we are going to discuss the uniform noise model. It means that epsilon follows uniform distribution in some range a comma b. So first we'll just give you a brief idea as to what uniform distributions are. So assume that we have a random variable z which follows a uniform distribution between A and B. It means that the probability density function of z, so P uniform of z, will be 1 over B minus A for z between A and B. It would be 0 for z greater than B and 0 for z less than A. So to plot this distribution, it would look something like this. Assume that this is A and this is B. This is Z and this is P of Z. So our distribution would be constant, so our probability density function. Sometimes we just use probability density function. We just call it probability distribution function. And we will clear the difference wherever it matters. So for this discussion, it wouldn't matter much. So the probability density function is going to be constant between A and B. And it is going to be 0 everywhere else. So it is 0 for any value less than A and is 0 for any value greater than b. So between a and b, this value is going to be 1 over b minus a. So this is what a uniform distribution looks like. So if z is a random variable which follows uniform distribution between the values a and b, then the probability density function or the probability distribution function is going to be 1 over b minus a for z between b and a, and is going to be 0 anywhere else. So in the uniform noise model, our noise at any pixel location follows uniform distribution in some range a and b. So for example, let's suppose we have the original pixel value f of x comma y and a small epsilon noise which follows uniform distribution between a and b. Then the resultant image value at pixel x comma y is going to the original image signal, original pixel value, plus some value between a and b. So we are assuming that this noise epsilon is spatially independent that is the noise doesn't depend on the location as to where it is being applied. Furthermore, the noise is also independent of the pixel values and the neighborhood pixel values of any pixel. So in a uniform noise model, we have pixels, original image pixels, corrupted by a uniform noise at any pixel location x comma y, and the noise, for example, the magnitude of the noise is independent of the pixel location. So the epsilon x comma y, we are using it to denote the value of the noise at location x comma y. It is independent of the location x comma y in an image. For example, whether x is 100 and y is 200, or x is 10 and y is 10, the uniform noise doesn't depend. For example, for each of these locations, the epsilon would be uniform, follow uniform distribution between a and b, where a and b are some values. For example, if we are using normalized intensity values, for example, the image values, pixel values are visited between 0 and 1, then we can assume that our epsilon follows a uniform noise between let's say some small values, negative 0.1 to 0.1. That is, each of the image pixels is going to change their values by some small amount between negative 0.1 and 0.1. And this A and B is independent of the location of the image, and it is independent of the pixel values. So we also assume that epsilon x comma y is independent of the pixel value and x comma y. It means that A and B means it's having a uniform distribution between A and B. So the value of A is independent of the pixel value and is independent of the location of the image. Similarly, B is also independent of the pixel value and is also independent of the location in the image. So next we are going to present an example of an image that is corrupted by a uniform noise.